In the introduction, I mentioned that deep learning sits in the artificial intelligence arena. But what is AI and how is deep learning different from traditional machine learning? Artificial intelligence has its roots in the 1950s when researchers started asking if computers can be made to think. At the outset, this basically meant symbolic AI. Artificial intelligence could be achieved by manually programming a sufficiently large set of explicit rules. Think checkers or chess. In symbolic AI, we use the data and the rules that govern them to program algorithms, which is basically what classical programming is all about. You have data and you know all the possible things that can happen, you just need the computer to follow the rules. But the problem with symbolic AI is that it's not possible to write explicit rules for solving more complex, fuzzy problems, such as image classification, speech recognition, and language translation. For this, you need a computer that can learn to perform a specific task on its own. In traditional machine learning, we feed in the data and in a supervised learning scenario, the answers, and we train the computer to develop the algorithm. It returns the rules on how to get those answers. There are a variety of tools that we can use, for example, a decision tree. This system has taken hold since the 1990s, and in recent years, as faster hardware, larger data, and more sophisticated algorithms were developed, deep learning emerged as a distinct subdiscipline. Finding rules that describe underlying patterns has been the domain of statistics and machine learning in one form or another for quite some time now, but deep learning was something new. We're still allowing an algorithm to define the rules that lead from the data to the provided answer, but now those rules can be much more elaborate and subtle. The deep in deep learning is referring to the layers of subtle rules that lead from the data to the answer. In traditional machine learning, we may have only one or two layers, but in deep learning, we can have dozens or more, each further refining the output of the previous layer. In addition to that, we allow each layer to be refined through a reiterative process that improves the algorithm in each round by monitoring some useful metric. Given this new paradigm, we can handle many analytical questions if we have three things. First, we need some input, which can take many different forms. Second, we need some output that we want to predict given the input. That's the answer that we've been talking about so far. And third, we need some useful metric that tells us how well we're doing. Here are some examples we'll see in this course, and which you may already be trying to do in your own work. Binary classification from an image is a computer vision problem, but is a similar question to binary classification from text. We're not really asking the computer to read, but we are asking it to tell us something about the input. Multi-class classification is another common problem, and we'll begin our work with this famous example of digit classification. Scalar regression can also be from an image, as we try to guess someone's age based on their photo, or more typically from multivariate data. So we typically want to predict some output based on the input. The metrics allow us to determine if the rules developed by our machine learning algorithm are actually doing that. If not, then we can go back and try and adjust them. So given all the different kinds of inputs, how is it that we end up with a generalist method that can handle all of this complexity? Well, regardless of what the input data is, a key concept we'll see throughout the book is that deep learning faces a central problem of meaningfully transforming data. Imagine this scenario where we have data described by two dimensions. If we want to define a boundary between the black and white group, we can look for the simplest geometric transformation that would allow us to find that. When we look at this neural network, all we're trying to do is develop an algorithm that allows us to learn the best representations of our data. And all we mean with that is, what are the transformations to perform in each layer that allow for the most accurate output calling? So if we think about our digits, we're just going to take sequential representations of the data and see that we can properly predict the output given the transformed input. That's basically what we were talking about in the introduction before the book. We want to find underlying patterns. The types of transformations that a machine learning algorithm can perform is called the hypothesis space. These are predefined operations such as coordinate changes like what we just saw, or linear projections, translation, nonlinear operations, and so on. So the easiest way to think about deep learning is as a mathematical transformation for learning representations from data, going through a series of information distillation processes. In each layer, information gets increasingly purified. Although machine learning has been around for a while, deep learning is a new solution to old problems and is at the center of the current hype boom. In the next chapter, I'll try and put that into perspective for us so that we understand the limitations of deep learning.